So, in the last lecture we were looking at radiative absorption in gases from microscopic perspective. We are trying to understand the role played by vibration rotation in creating this complex structure of the radiation bands, and we saw that there are these vibrational transitions which come along with rotational transitions, which lead to three branches: the Q branch, which is purely vibrational transition, R branch and P branch. And in R branch the frequencies are higher because there is both a positive vibrational energy change and rotational energy change. In the case of P branch, the vibrational transition is upwards and rotational is downwards. So, the frequency is lower. And then we saw that if the gas temperature is high, the transition can occur instead of one level, it can be two levels, and these are called overtones, and these are important in high temperatures, especially in furnaces. We saw examples of various gases, and we pointed out that symmetric diatomic gas like oxygen and nitrogen have essentially no absorption bands, because there are no permanent dipole moment, and when they vibrate they do not have a dipole to interact with the electric field. So, they do not absorb or emit radiation. On the other hand, asymmetric molecules like carbon monoxide and molecules like carbon dioxide, which are linear triatomic, or nitrous oxide, and water vapor, which is nonlinear molecule, ozone and methane, they all have absorption bands in the infrared. And the way these bands are generated is based on either symmetric stretching or asymmetric stretching or bending. And we saw the various frequencies at which these absorption bands occur. We saw examples of the symmetric stretching, asymmetric stretching and bending. And we saw that the stretching frequencies are higher because more energy is required to stretch than bend. And this is a typical vibration rotation band consisting of hundreds of lines. And so, this is the challenge one faces when solving a problem in radiation, that the absorption is a strong function of frequency or wavelength, and the variations are very rapid. For example, you have extremely high absorption at one wavelength, and immediately there is no absorption in the frequency between the two bands, between the two lines here. So, this is the factor we have to contend with, that we have a quantity which varies extremely rapidly with frequency or wavelength. And so, when we integrate the radiative flux, the spectral radiative flux to get the total radiative flux, we have to use a extremely fine resolution to capture the strongly absorbing as well as the weakly absorbing region. Now, today in principle this can be done because of the availability of computers, but it is not done routinely, it is done more for basic research. So, you can integrate through all these individual lines by using extremely fine frequency spacing in the integration, and you can capture all the radiation absorbed in these lines and radiation which is allowed to be transmitted between lines. But our aim is to come up with a somewhat simpler method of solving. The so called line by line integration in principle is doable, as long as you use a frequency step in the integration which is smaller than the spacing between two lines. So, there are these lines and there is spacing between lines, and as long as your integration step is smaller than the spacing, you should be able to capture this. But remember that one of these vibration rotation band has hundreds of lines, and there are many bands, and in a typical example in the real world you will have many gases: carbon dioxide, water vapor, methane, ozone, and so each one of them are many bands, and each bands are hundreds of lines. So, the total amount of lines you have to integrate through is very large. And so, although in principle you can do an integration over wavelength by taking extremely fine wavelength interval, in reality this is not done routinely. We saw the example of these lines as it exists, and what happens to these lines when there is collision with other molecules which makes the line broader. So, the unusual feature of radiative heat transfer is, suppose you consider a medium containing carbon dioxide and nitrogen. Carbon dioxide is a gas which absorbs infrared radiation, nitrogen does not. And let us assume that there is a given amount of carbon dioxide in a container, and the carbon dioxide and nitrogen combined total pressure is, let us say, 1 bar. Then you increase the amount of nitrogen in the container by pumping nitrogen in and increase the total pressure 2 bar. You do not change the amount of CO2, but change the amount of nitrogen, which is a non-absorbing gas. You would normally think that addition of a non-absorbing gas should not alter the ability of carbon dioxide to absorb radiation, but it does, because these additional nitrogen molecules will collide with the carbon dioxide molecules and broaden these lines substantially. So, we saw that the typical collision broadening function is like this, and so if you in this function nu 0 is the center frequency and alpha is the line width, and this line width is a function of total pressure. The line width depends on total pressure, and so if you increase total pressure by adding a non-absorbing gas, you will change the line width and hence change the ability of carbon dioxide to absorb radiation. So, this is an unusual paradox which you do not find in many other fields, that is, a molecule which does not absorb radiation by itself is able to alter the radiative heat transfer pattern by merely colliding with the molecule which can absorb radiation and changing the character of that absorption phenomena. So, this is an example of an indirect impact of a gas like nitrogen. And we also saw that in addition to collisional broadening or Lorentz broadening, which is caused by collision between different molecules, there is also broadening that occurs because molecules are traveling at quite high speed, and so the frequency of the emission by the molecule that we see in the laboratory is different from the frequency as we see sitting on the molecule. And so, this Doppler broadening depends strongly on temperature. You can see that the half width for Doppler broadening is alpha d, and alpha d is proportional to square root of temperature. So, at high temperature the width is much larger than at low temperature. And we saw the typical profile of the Doppler broadening and Lorentz broadening. Doppler broadening has a Gaussian profile and hence it steeply falls to 0, while the Lorentz broadening goes 1 over 1 plus x squared. So, it goes down with frequency at a much slower rate, and so you can see that we can have situation wherein the Doppler broadening dominates near the center of the line, while at the edge of the line Lorentz profile dominates. So, if such a situation occurs, then you have to use a more complicated shape which are the shape of the Doppler profile near the center line, and then you pick the Lorentz profile. This is called white profile, and it is used in those situations where the Doppler broadening dominates at the center of the line and Lorentz broadening dominates at the wings. And this figure shows the important effect of pressure on the line width. You can see that the line width, which is only 0.0125 centimeter minus 1 at low pressure like 1/4 bar, as the pressure is doubled, the line width is doubled, and again pressure is doubled, line width is doubled. So, you can see that line width in this case increases linearly with pressure, and that is why in the Earth's atmosphere Doppler broadening dominates at low pressure above about 80 kilometers, while pressure broadening is what you will see at the lower elevations. For oxygen, for carbon dioxide beyond 40 kilometers, you can see the Doppler broadening dominates, and below 40 kilometers the pressure broadening dominates. And here is a typical example of a water vapor absorption band at 820 nanometer, showing presence of thousands of lines with pretty complex behavior, and the smoothened picture is shown here. In the older spectrometers that were used 30-40 years ago, you would only get that smoothened profile, you will not get the individual lines. Today you can identify the individual lines either using a high resolution spectroscope or by using software which generates these lines based on knowledge of quantum mechanics and experimental data. Now, we are going to show this figure enlarged slowly. Now, this is going from 780 nanometers to 860 nanometers, 80 nanometers. Now, we have a close up where now you look at only 8 nanometers. So, 10 times you amplified the figure, and now you are beginning to see the individual lines and the spacing between lines, and this is where we see that we have to integrate very carefully, because this gas water vapor is almost transparent in a certain wavelength, and in the adjacent wavelength almost opaque. So, there is a rapid transition between opaque to transparent to opaque, and if you use a very crude resolution, you will get this figure which is shown here, and that can sometimes give misleading answers. So, for accurate estimate of fluxes, it is important to use as high a resolution as is practically feasible. And now we look at the same spectra again. Now, instead of 8 nanometers, looking at only 0.4 nanometers, very high resolution. This one comparing the observed spectrum with the simulated spectrum, showing that the simulations have reached fairly high level of accuracy, is able to identify each line in this band and showing a large spacing between the lines. Now, we show once again the impact of pressure. We start with 1000 millibar, we get the full carbon dioxide spectrum at 670 centimeters minus 1, and then we look at a close up of the absorption band right close to 667, and you see that this thing has slight waviness, and that waviness is there because of the lines, but these lines are not fully resolved. So, if you now go to 100 millibar where the pressure broadening is much weaker, these lines are visible clearly. So, these lines are visible at low pressure, are not visible at high pressure, because the line width increases so much that it completely blocks out the space between the lines, and you get a fairly smooth function. So, if you are dealing with this problem at 1 bar pressure, then of course, you can easily calculate this by using a fairly crude integration. But if you are dealing with this situation, you have to be very careful how you integrate this transmission to get the actual result. And one more example we have given of oxygen absorption coefficient in the microwave for low pressure or high pressure. You can see that in the low pressure you see all the high resolution fluctuations, while at high pressure all of these get smeared out and you are getting a fairly smooth profile here. And lastly, we see how the atmospheric measurement of carbon dioxide emission by satellites. The oldest satellite had extremely poor resolution, about 50 centimeter minus 1. So, could not really resolve the carbon dioxide spectrum in 720 or 15 micron band, but the next satellite IRIS had a somewhat higher resolution. It was able to identify 2 of the lines, and finally, we have very high resolution infrared sensors. They are able to resolve many of the lines very clearly. And the impact of all the absorption on the solar radiation is shown clearly here. The orange line is the emission at the top of the atmosphere, which is fairly smooth, close to a black body at 5018 degrees Kelvin. And now we look at bottom of the atmosphere. The blue curve is much more complicated because of the absorption bands of various gases like water vapor, which are there in the infrared in the solar region. And more information is available about these impact of these gases by looking at the radiation measured from the satellite in the region around Sahara, and you can see that broadly there is a black body spectrum at 3 millibar influenced by absorption by the carbon dioxide band here at 15 micron, ozone band at 9 micron, and other influence of water vapor here and here. And can clearly see that carbon dioxide is such a strong absorber that the emission from the earth in the carbon dioxide band is coming not from the surface at around 300 K, but from the tropopause at around 200 K. And here we compare the difference between Sahara desert and Antarctic ice sheet spectra as seen by satellite, and you see that the carbon dioxide dip you see here in Sahara is seen as a rise. Now, this is very surprising result, and it only gives you a hint that in Antarctica there is a very strong low level inversion, and hence when you sense this region through the absorbed band of water vapor, you are sensing the emission not from the surface, but from a certain height, and if there is inversion, that height will have high temperature and hence will have high radiance. Now, let us look at a few important nomenclature that we used in this subject. The amount of absorbing gas can be expressed in many ways. You can express in terms of grams per centimeter squared the amount of the absorbing gas available in a column, that nothing but density multiplied by the length scale. So, that is a fairly common method. The other method is centimeter atmosphere. It is called a pressure path length. You calculate the amount of absorber by looking at the amount of absorber that is present along a path per unit pressure. And so, these are common units used for the amount of absorber as well as absorbent coefficient. Now, this figure clearly illustrates the important difference between the solar region and the IR region. You can see in the infrared region beyond around 0.7 micron, there is a lot of absorption by the atmospheric gases, H2O, carbon dioxide, ozone and so on. And on the other hand, below around 0.7 micron, atmosphere is almost transparent. Of course, this is the basis of the greenhouse effect. Now, here is a sample of various molecules which absorb and emit radiation in the wavelength range from 7 micron to 15 micron. You can see there are a large number of gases, mostly man-made, which have been emitted during industrial activities and which remain in the atmosphere a certain amount of time, and during that period they interact strongly with the radiation leaving the ground. So, this has to be documented in order for us to estimate the warming caused by these. Now, next we move on, we got a general picture of how the molecules behave. Let us look at a few more examples to illustrate. Here is the absorption coefficient of air at 12,000 degrees Kelvin. Notice that in comparison to what you saw for carbon dioxide, water vapor and so on, where the absorption coefficient had a very complex structure with wavelength, here it is a fairly smooth function. As a matter of fact, one look at this and one can assume that you can assume air at 12,000 Kelvin to be a grey gas with a constant absorption coefficient. You will not make too much error. The question is, why does air exhibit such a smooth dependence on wavelength or frequency, while the other examples we saw were all much more complex. To understand that, we need to know the kind of transition that is going on here. In the case of gases, the vibration transition that we saw are all bound transition, that is, it goes from one bound state to another bound state, and the energy it can absorb is precisely fixed by the equation delta E equals h nu. On the other hand, if the temperature is sufficiently high, molecule can jump from a bound state to a free state. In the free state, the kinetic energy of the molecule can be anything, and hence you absorb radiation continuously with no gap in between. So, this is of course advantageous from the point of view of analysis, because if the gas is undergoing bound free transition, then the assumption of a uniform absorption coefficient is a very useful technique, does not demand too much computer time, and you can actually check that even if you did complicated non-gray assumptions, the final answer you will get will not be very different from what obtained by assuming this to be a gray sample. Now, let us do an example now of carbon dioxide. We saw that of air, which are continuous spectra. Now, look at the absorption band of carbon dioxide at a fairly high temperature, 830 Kelvin, typical situation that kind of furnace at a fairly high pressure, and the gas is at 10 atmosphere pressure and in a container of the length scale 38.8 centimeters. So, you can see that there are 4 major absorption bands. Actually, there are more, some of them are not visible because they are overlapping. Actually, in this figure is a 10, 15, 10.4, 9.4, 4.8, 4.3, 2.7, 2. So, of these you can see that 3 of the bands are overlapping here and 2 bands are overlapping here. So, it is a fairly complicated problem, because if 2 bands are overlapping, then you have to correctly account for the absorption by each band. So, this is typical behavior of carbon dioxide. Now, finally, we need to estimate emissivity of a gas, and so we will ultimately integrate over wavelength and get an idea of the emission, and that is best done by using charts. So, I realize that charts are not that common these days, because you have calculators and other tools available to calculate anything to the highest accuracy, but it is still a very useful tool to have a chart, because you can do one set of hand calculation to ensure that you have a good understanding of what is going on in this problem. So, here is the total emissivity of water vapor as a function of gas temperature for various path length, and the path length in is an atmosphere centimeter, and you can see that as the temperature increases, the emissivity of the gas goes on decreasing, and notice that even at the highest path length, the emissivity does not cross 0.7. So, that has to be kept in mind. Here is the emissivity of carbon dioxide as a function of wavelength, as a function of gas temperature, I am sorry, total emissivity, and these are various path lengths, starting from 0.01 to 0.006. And you can see that there is a region where the emissivity is not varying much, but there is another region where emissivity is falling fairly rapidly. Now, one of the challenges in dealing with radiation in furnaces is the problem of overlap between lines, between a line and another line. So, these are issues which you have to deal with when you want to deal with non-grain nature of medium. Now, first we will define emissivity of a gas, and as you recall, emissivity of a gas can only be defined for an isothermal gas layer. The layer is not isothermal, you will have great problem in defining emissivity. And so, emissivity, as we have already defined for surface, the same logic, is 1 by Tg to the power of 4 integral 0 to infinity 1 minus e to the minus a omega L d omega. And once you are given the value of a omega, then you calculate the function, then integrate over the wavelength of wave number. It is worth remembering that since a omega is a very rapid and complex function of frequency or wavelength, we have to make a decision how we calculate this quantity in a given situation. Now, remember that we have to have E b omega that I forgot, and this E b omega with T s, gas temperature. On the other hand, if you want to have absorptivity of radiation coming from a black body, then we need to know the source temperature, and then we can ask how much of this radiation emitted by that source at that temperature is actually absorbed by the gas. So, this is similar to what we already done for surfaces. So, when we got emissivity, it was only function of the surface temperature. In this case, the emissivity will function of the gas temperature, but absorptivity will be function both of gas temperature as well as the temperature of the source. So, the source will determine how much gas will absorb. Now, what does this emissivity depend on? Now, this emissivity depends on, as you can recall, has to depend on the amount of absorbing gas in that region, the appropriate length scale. It will depend on gas temperature, and it depends upon the exact vibration rotation land structure, which you might say as B by D being line spacing by normally written as line width by line spacing. So, what we see is that the emissivity of gas depends not only on the amount of matter along the path, which can be amount of, this will be in typically kg per meter squared. This tells you how much absorbed molecules are there along your path of interest to you, and it also depends on, of course, gas temperature. So, our aim now is to ask, if you do not want to integrate the original spectral data line by line, is there an alternate way to formulate the problem in terms of emissivity and obtain this function either through experimental data or by using data from a line by line code and creating a emissivity database. So, both can be done, and depending on the situation, either the two methods is used. And in the same token here, the absorptivity of a gas is a function of the absorbing gas, of course, length scale, line structure parameter B by D, and the gas temperature as well as the source temperature. So, absorptivity, as expected, is a bit more complicated than emissivity. Emissivity on integration depends only on the temperature of the gas, while absorptivity depends both on the temperature of the gas and temperature of the source from which radiation is emitted. That also influences your absorptivity of the gas. Now, how do these emissivity charts look like? I will give you examples and we will take up a detailed presentation later. So, we will merely have a look at the kinds of emissivity charts that are available. Here is an example of emissivity chart of water vapor. X axis gives you the temperature in degrees Kelvin. The y axis gives you the emissivity going all the way from 0.007 to 0.7 and a factor of 100 increase here, and it is shown for various amounts of the carbon dioxide they are available, that is water vapor available, water vapor partial pressure into the length scale. And one notices that for a given length scale, as you increase temperature, the emissivity of the water vapor comes down. This can be understood in terms of the fact that as the temperatures increase, the peak of the black body function starts shifting to a lower wavelength. according to the Wien's law. So, at 400 degrees Kelvin, your peak of black body spectrum is around 7 micron, but as you go to 2800 it will be around 1 micron. So, as the band shifts towards the lower wavelength, there are not too many absorption bands of water vapor, and hence the emissivity comes down. So, this can be understood very simple terms based on the knowledge about spectroscopy data. Here is an example of carbon dioxide, which whose emissivity goes from 0.003 to 0.3 and temperature of 400 to 300 K, and once more we see that there is a region where gas temperature does not influence the emissivity too much, but at very high temperature once more all the radiation from the black body goes to lower wavelength regions, and hence the emissivity starts falling, because these bands which we discussed today did not really able to utilize the database that may be available. Now, if you are dealing with pure water vapor or pure carbon dioxide, or these mixed with nitrogen which does not absorb, then one can proceed and use these charts. But if so, now we ask ourselves, what if you have a mixture of gases, which is quite common in furnaces or in atmospheric application. Let us say we have mixture of gases containing both carbon dioxide and water vapor. Then we cannot get the gas emissivity merely by adding the carbon dioxide emissivity and the water vapor emissivity. We must account for the fact that the various absorption lines of water vapor and carbon dioxide can overlap, and hence we have to subtract the contribution due to overlap. This is inevitable. In addition, if you are going to use a chart which uses standard pressure conditions, and your situation is such that the pressure in your furnace or other appliance is not the standard on bar pressure, then you have to add correction terms. So, this is correction for P total not being equal to 1 bar. So, that is what is shown in the other figure here. We see here the correction chart for carbon dioxide when the pressure is other than 1 atmosphere. If the total pressure goes to as low as 0.05 atmosphere, correction can be as low as 0.3, while you go to high pressure like 5 atmosphere, the increase in emissivity can be 50%. So, both these situations occur in real world. There are furnaces with pressures below atmosphere, and there are situations occurring in diesel engine and other devices where the pressure go to very high values. Now, there is one more correction here due to overlap, that delta epsilon term, and here is an example how you do the overlap correction at various temperature 400, 810 and 1200 K, and you can see that the correction for epsilon is of the order of 0.01 to 0.05, and it depends upon the total amount of absorbing molecules in a path, and in either extreme of course the correction is not there, because you have either pure H2O or pure CO2 here. So, these are charts have been routinely used by engineers to calculate performance of furnaces and boilers. Of course, today these will be now available in the form of equations or software and not charts, but charts are still good to use because they give a physical insight into the kinds of accuracy and inaccuracy that may have encountered in your calculation. Here is a correction chart for water vapor if it is not at the total pressure of 1 bar. Now, there are other charts available by various other investigators, and I must mention that these values from different charts can differ by as much as 10%. This is quite common. So, you can see that these overlap correction can be of the order of 0.05, and these can be as a 1.5 as low as 0.3. So, ultimately you will get an estimate of epsilon g, and depending on which chart you use or which source you use, there can be variation of the order of 10%, which you must accept as error. Today, of course, all these are available through software and they are calculated, but as a student it is important that you do this hand calculation once, so that you get a physical feel for the kind of error introduced at various stages in your calculation. Now, this is one approach that I pointed out. There is one more approach available. This approach, you calculate emissivity of gases, is an old approach, but with more accurate data available for various bands of various molecules. Now, there are attempts to have this done little more accurately, and I will give you an example here. We saw that the emissivity of the gas goes as integrated over wave number So, this integration over all wave numbers can be split into integration over specific bands of, let us say, carbon dioxide, and calculate these quantities per band, and then average over all bands. Now, the reason why this is popular is, if a given band is not too wide, then this quantity can be taken out. This will not vary a lot unless the band is very wide. So, you can write this as at the center of the ith band, and then you have a simple integration only of the absorption coefficient. So, this integration is easy to perform because the black body function has been separated out because it is slowly varying, and this is available in many sources. This is called the band absorptance of the ith band. So, to remind you, band absorptance of the ith band is equal to integration over the ith band of the absorptivity or emissivity of that band only. And once you do that, you calculate emissivity as sum over all the bands I1 to n, let us say there are n bands, and calculate the black body function at the center of the ith band, and you have the A, B, I, which will be a function of the partial pressure of the gas times the length scale involved, something called the line structure parameter, which we will define now, and gas temperature. the line structure parameter I is nothing but the line width of the ith band by line spacing. So, this will play an important role in determining absorptivity of the gas, because if the line width is small compared to line spacing, that is beta I is much less than 1, you have essentially non-overlapping lines. While if beta I is much greater than 1, then you are completely overlapping lines. And you can see that in this second limit, which you can expect will occur at high pressures, the detailed structure of the lines will be smeared out, and so the problem will get simpler. In the other extreme here, when the lines are completely non-overlapping, the line spacing is a very important parameter. And so visually again let us highlight it. Beta I is much less than 1, is non-overlapping, and so there are lines which are individual and separate. If beta I is much greater than 1, is completely overlapping. So, it will be like this. So, you expect the behavior of the gas to be very different in these two extreme cases, and we can illustrate the result through some examples that we can take up. And I will take an example right now to make this point by looking at a carbon dioxide gas. So, let us take an example to illustrate these issues. We have a carbon dioxide gas, total pressure is 1 bar, it contains 20% CO2, 80% N2. This is a typical situation in the case of furnace after combustion, mostly it is CO2. Let the length scale be about 5 meters, that is the distance between the walls of a furnace. Let the gas temperature be of the order of 1500 degrees Kelvin, typical of furnace example, and the wall temperature which is 600. All these numbers we are given are ones which occur quite commonly in furnaces. The wall is kept cool because of the water boiling, and the typical temperature of the furnace gas is 1500 K. Now, in this case, how will this calculation for these various quantities look like? Now, remind you what you can write. You try to calculate epsilon g, which if you recall is equal to sum over all the bands of EB omega I by sigma Tg to the power of 4 into ABI, which is a function of the pressure path length of carbon dioxide, gas temperature, and the line structure parameter beta. If you come to calculate absorptivity for a radiation from a source, then you will sum over all the I bands, but you calculate the temperature of the source by sigma Ts to the power of 4. This will be I am sorry of Ts. So, this is the fractional radiation coming from a source. you still look at ABI, this factor is same. So, the key point to note is that absorptivity depends both on the source temperature and the gas temperature, while the emissivity depends only on the gas temperature. So, this I want to remind you is similar to what happened in metals. Metal also we saw emissivity function only of Tg, while absorptivity depend on both Tg and T source. So, this comes out nicely. Now, let me calculate this for this example we have just now taken up. I will deliberately do all the calculation for various wave numbers, and so that you understand the contribution of various bands. So, this is the center of the band, it is centimeter minus 1. This is the band absorptance of the band, and the contribution E B omega by sigma T to the power of 4 into A B, and then you have E B omega by sigma T s to the power of 4 A B. So, these two are the contribution for absorbed emissivity. The bands are considered are 15 micron band, 10.4 micron band. Band is represented by the wavelength in micron. So, I have considered here about 3 plus 3 6 bands, okay, and their centers in wave number space is 667, 960, 1060, 2349, 3660 and 5220, and the band absorptance at these wave numbers are for these proper conditions 312, 210, 170, 343, 384 and 49. Now, straight away from this particular column, you see that the strongest bands of carbon dioxide are the 4.3 and 2.7 micron band for this condition of temperature and path length. But how much they contribute to emissivity and absorptivity is very different. You have to multiply this by this fraction. For emissivity, you get following contribution. You add all this up, you get 0.18 as the gas emissivity. So, emissivity of carbon dioxide gas, in spite of its strong absorption in the 4.3 and 2.7 micron band, is only 0.18. Okay. So, that is typical of gases. Even if you put a lot of gas in a container, the reasonable path length, you will not get emissivity like 0.8, 0.9. Now, the same situation, when you ask what is the absorptivity, you have to worry about the source temperature, remember, not the gas temperature, and so all the numbers will change. Here it goes up 10 times, this also goes up 10 times, this is also higher, this band also is higher, and this band is lower, and this band is nothing. Now, why is that? Because when you look at the radiation from the source temperature, which in this case is 600 Kelvin water wall or the furnace. So, the peak emission from that 600 Kelvin source will be around 4 micron, 5 micron, something like that, and so it will fundamentally alter the character of your result here. And if you look at the absorptivity, it is more like 0.41. Okay. So, you see that the absorptivity of the gas versus the emissivity, they are very different, factor of 2, because the contribution from various sources is very different. Now, you can see that in the case of emissivity, the major contribution came from here. In the case of absorptivity, the major contribution came from here. And so, that is the fundamental difference between the two situations. And so, this clearly illustrates the fact that absorptivity and emissivity of gases can be very different, and hence these, to treat them as a gray gas is not a good approximation, and non-gray model is always better, but we saw non-gray model is difficult, and hence we need to make some approximations, and these will be discussed in the next lecture.